Okay. So basically what we're going to do, this is for AP Physics C, Mechanics, Conservation of Energy. This is page 239 of the textbook, question 39. So first thing we're going to do is we're going to draw a little diagram of the question. So if you read, there is a 3 kilogram box at a height of 5 meters that is dropped onto a slope, and there's a spring down here. Don't judge my spring. So what we're gonna have to go through is, first we're gonna figure out the equations that we need. Then we're actually gonna plug in the values to find out what the compression of the spring is once this 3 kilogram box hits the spring. And then there's a second part we'll get into after that. So according to the conservation of energy, the energy initial must equal the energy final. So basically whatever energy you have up here must equal the energy down here, whether it's potential or kinetic. So the two equations that we need to know, first one is potential energy equals mass times gravity times height. So that's just potential energy for anything that is suspended above the ground. And then the second thing we need to know is the equation for spring potential energy. And that is 1/2 K, which is the spring constant, X, which is the compression of the spring, the distance, squared. So those are the two equations that we need to know. And so since they have to equal each other, according to this, the initial situation is the box up here. Once it travels down here, the final situation is the compressed spring. Like that. So we can set up this equation like so. MGH, which is energy initial, must equal 1/2 Kx squared. And I forgot to mention, the book does already give you the spring constant. So the K in this scenario is equal to 400 Newton over meters. That's poor handwriting, but I'm sorry. So now it's just a matter of plugging everything in. So you know the box, the mass is 3 kilograms. So plug that into mass. You know, acceleration due to gravity is approximately 10. And you know the height of the box, just vertical height, is 5 meters. And so then you can set up the other side of the equation. You know K, which is given to you, is 400. And you're trying to find X, so X will remain as a variable. So now you have one variable in this equation, and it's just algebra from there. So you multiply this out, and you get 30 times 5, which is 150, equals 200x squared. You just divide. 150 divided by 200 is 3/4, equals x squared. And then you take the root of both sides, and it comes out to √3 over 2. And if you plug that into your calculator, it's 0.866. And so since this is in meters, that's the unit that you have to put onto the end of it. Okay, so now that we've completely revamped our video station, we're just gonna go through real quick the second part of this equation. Since the energy initial has to equal energy final, that can also be written as energy final is equal to energy initial. So whatever happens, if it retraces, or whatever happens after it hits the spring, it has to retrace to be the exact same height, because the energy down here, the spring potential energy, has to equal the potential energy due to gravity. So it'll just go right exactly back to the place it was, and then just be in an endless cycle.